So this is another example of Hess's law and what it means. And we're all talking, when we talk about Hess's law, it's the summation of the energy that's in compounds. It's there. It's a part of that compound. How we liberate it, what we do with it is what we're kind of trying to talk about. And there's two ways that I can do Hess's law. One of them was the heat of summation, where I showed you in the last video where it was the sum of the products minus sum of the reactants. This is another one that takes place. Oftentimes, you're forced to do this because you can't figure out any other way to figure out the heat of a reaction. And you take the sum of two reactions, or three reactions, or four reactions, multiple reactions, and you algebraically add them together and you find out what you're looking for. So here's a case. Let's say you're given carbon and oxygen. So it's a combustion reaction, and that is going to form carbon dioxide. Okay, that's a gas. That's a gas. And it turns out that the delta H for this reaction is equal to a negative 393.5 kilojoules. Numbers aren't looking very good. Kilojoules, okay? And you're given another reaction where two carbon monoxides in the gas phase are going to burn with oxygen, and it's going to produce two CO2s, where the delta H for this reaction is equal to minus 566 kilojoules. All right? And what I want to determine out of those two is this reaction. We have carbon, solid, plus a half an oxygen. Now, I haven't done this in the videos before, but it's common to balance equations with fractions, because many times you're trying to find the product in terms of 1 mole. So you can balance, the rules for balancing are, it's the same thing, you can just do it with fractions. So now I want to figure out what the delta H of this reaction is going to be from manipulating these two reactions, so that when I add them up, I'm going to get the one that I want. All right? Well, the way to do this is to sort of set up a ground rule. If I'm looking at carbon monoxide right here, okay, as a product, right there, I look up at my two equations up here, and I figure out, and you could have 3, 4, but this particular example just has 2 to keep it simple. I look for the carbon monoxide. Carbon monoxide is right there, all right? Now, it happens to be on the wrong side. So what I'm going to do is I am going to reverse this. Reverse that reaction. I'm going to flip it around. Now, I'm also going to be looking at, okay, I have, the other thing I'm kind of looking at is there's carbon right there. Well, the only reaction up here that has carbon is this one, and it's in the right place. So I'm not going to have to reverse it or do anything with it. But I'm looking at this, and I can already see a little bit of a problem. I want to cancel out carbon dioxides. Okay, I will want to do that. Here I have 2 carbon dioxides right there. There I have 1, so I'm probably going to have to manipulate this a little bit more. And I'll show you how this works. Okay, so the first reaction, I'm not going to do anything to. It was simply carbon, because carbon was in the right place, solid, plus O2 going to CO2. And the delta H for that was minus 393.5. Again, that's exothermic, and that's what you'd expect from a combustion reaction. When you burn something, it gives off heat, so that negative sign is right there. Now this other one, when I said to reverse it, all right, this equation right here, I'm going to reverse it. I'm going to write 2 CO2s first, then the rest. When I reverse it, I need to change the sign on the heat. And this is what I described in the first video on Hess's law, or on thermochemistry. It's one of the rules of thermochemistry. All right, so I am now going to write 2 CO2 gas going to 2 CO gas plus O2 gas. And the heat coming out of this now becomes a positive 566 kilojoules. All right, there are kilojoules. I'm running out of space. Put kilojoules there. All right. So the trick is I reverse the reaction and I change the sign on the heat. So these are the rules of thermodynamics. Now when I look at this, I'm going to want to cancel out the CO2s. Trouble is, I have 2 CO2s there, I have 1 CO2 there. One of the properties of thermochemistry is that the amount of what you have in heat is proportional to the amount of reactant or product. So I'm going to take this value and I'm going to divide this whole equation by 2. I'm going to simply divide everything there by 2. Okay? So when I do that, that's going to give me CO2 gas going to CO gas plus 1/2 O2 gas. Now because I divided that in 2, all right, I divided the reaction in 2, I have half as much, I'm representing half as much reactant there. I need to divide the amount of heat by 2. So the amount of, if I divide 566 by 2, I come up with 283 kilojoules. And it's still positive. I haven't changed that. Okay? 283 kilojoules. Now I can take my first equation right here, drop it down. Carbon solid plus O2, which is a gas, going to CO2, which is a gas. And that amount was minus 393.5. What I'm going to do now is I'm going to add these two together. All right, and I'm going to cancel out those compounds or elements that are the same on both sides of the equations. This is just like adding 2 equations in algebra. It's exactly the same thing. We can do this because the heat is in these compounds. It's there, and I'm just rearranging it how I'm utilizing it. So if I look at this, all right, right here I have an oxygen. Okay, there I have 1/2 of an oxygen. So I can cancel that half of oxygen with half of this oxygen, leaving behind 1/2 O2. Here I have CO2 on the left side, and I have CO2 on the right side. So now I'm going to add these two together, dropping it down. Carbon plus 1/2 O2 is going to produce carbon monoxide. Now that was the equation that I was looking for. Okay? Just to remind you, here it was. I was shooting for this guy. Okay? And I did that. Alright? That is the same as what I got right here at the bottom. Now, what I do is I add the enthalpies together. So it's going to be 283 minus 393.5. The answer is going to be a negative 110.5 kilojoules. So I figured out the heat of this reaction from the sum of 2 separate reactions. Okay, so if I burn a mole of carbon and a 1/2 mole of oxygen, I get a mole of carbon dioxide. It is going to give off 110.5 kilojoules of heat. So we're going to practice this because we need to do this for a lab. So we'll do some of these in class.